All right, so what all of this boils down to, everybody, is the absolute value of a function as a graph can be graphed, and the properties of the graph can be determined by looking at the graph of the function before the absolute value is applied, and then simply folding anything that's below the x-axis above the x-axis. So as an illustration here, we can start off with functions that you're expected to know the graphs of without looking at a calculator. If I were to take a look at f, where I have h of x equals the absolute value of negative 3 times x plus 2 quantity squared minus 4, what I would do to determine all of the properties of that function is I would first ask myself, what are all of the properties of the graph of this function without the absolute value? Well, this is already in vertex form, so I know the vertex is at negative 2 comma negative 4. This is a very unique situation. I also know the parabola opens down, so I don't have to worry about any x-intercepts. It's too bad that it's written in vertex form because I can't determine the y-intercept just by glancing at it. If we had something like c, I can look at that and go the y-intercept of that function inside is 2. Here I can't, but I can figure out the y-intercept by replacing x with 2. So I'm just trying to get a little bit more information about this graph. The y-intercept will be equal to f of 0, which means we're just going to put in 0 for x. And we figure out what this is, and it's going to be a pretty big negative number. 0 plus 2 is 2. 2 squared is 4. 4 times negative 3 is negative 12. Minus 4 is negative 16. So what this graph will look like, and because it's negative 16, I'm just going to rescale things and say that it looks like this, where this is negative 16. This is the graph of f of x, which I hope you can appreciate and notice there was no f of x in the question. I made that up so that I could look at the graph of the function before the absolute value. So what does the graph of h of x look like? Any point on that graph that I've just drawn, which is the graph of f of x, any point below the x-axis gets reflected above. So in fact, every point on this question will be reflected above, because every y-coordinate is negative, which means that this is going to look you get the idea. Will look like that. And something I want to introduce to you right now, even though we're not going to use it, but I hope you'll remember it from this year to next year, is when we go from y equals f of x to y equals the absolute value of f of x, what is always happening is any point on f of x becomes this point on the absolute value. We are always absolute valuing, if that's a verb, we are always absolute valuing y. If y is positive, we absolute value it, it stays positive, it doesn't move. If y is 0, we absolute value it, it'll still be 0, it doesn't move. If y is negative, though, when we absolute value it, it becomes positive. All right, that will work with any function, whether it's quadratic, linear, or anything else. Does anybody have any questions you would like me to go over? 1b. Okay. So all we are asked to do here is create a table of values for the absolute value of the function. And this is a little strange because you don't know the equation of the function, right? But you do know that this column that we're going to add is the absolute value of the function. And this column is the function. So the column that I'm indicating right here is what's inside of the absolute value function in the third column. In other words, everybody, we're back to what I just said, that when you go from f of x to the absolute value of f of x, since f of x is y, we go to the absolute value of y. In other words, all we have to do here, Seamus, to complete this column is note that when x is negative 2, f of x is 0, so the absolute value of f of x will be the absolute value of 0. When x is negative 1, f of x, which is the y coordinate on the original graph that's inside the absolute value functions, is negative 2. So the y coordinate for the absolute value of the function will be the absolute value of negative 2, which is 2. Are you getting the drift here?
Yeah, but I just got confused by the two negative 2's. I didn't know if I was doing something wrong.
Well, no, because parabolas do this. So it's possible, I don't know where this is exactly, but it's possible for this to be negative 1, this to be negative 2. So there's a point here and a point here that are both negative 2. They don't have to follow some pattern that's going up by the same amount or down by the same amount. If these y coordinates do increase by the same amount regularly or decrease by the same amount regularly, then it's a linear function, that's all. But remember yesterday I talked about the graph of y equals sine of x that goes up and down and up and down. So these numbers could be going all over the place. The y coordinates can repeat. The x coordinates can't. That's a problem. Any other questions? All right then, we are going to move on today and look at the second part of this section, which deals with absolute value functions. But we will be exploring something called a piecewise function. Sorry, I just had to open up a file. So we're looking at 20.7.2 absolute value functions. This is part 2. This is still section 7.2 in your text. We're going to be writing an absolute value function today as something called a piecewise function. This is our only goal today. I give you an absolute value function. We have to write it in pieces. Okay? Somehow. The first thing I want to remind you of, and I've talked about this already, but it hasn't been formally in your notes, is that the absolute value of a negative quantity is negative 1 times that quantity. That just came out of my brain verbally. I'm going to turn around and look at what I typed. The absolute value of a negative quantity is equal to the negative of the quantity. Just think about that. What am I saying? I'm saying the absolute value of a quantity, if, I better do this, where the quantity is negative, is equal to negative of the quantity. What? Does that make sense? Well, it should, because the absolute value of negative 3 we know is 3, isn't it? We know that. This quantity in the absolute value sign, negative 3, is less than 0. What I am telling you is this should be equal to negative of that quantity. The quantity is negative 3. It has to be equal to negative 3. It has to be equal to positive 3. Another way of putting this, everybody, is to say, and we don't have to do this until today, is to say that if you're taking the absolute value of something which is negative, you have to take that thing that's negative and multiply it by -1 to make it positive. That's what that statement, the very first statement that's at the top of your screen, is saying. It's not how you would figure out the absolute value of -3 is 3. You just say it's 3. But what you're really doing, whether you realize it or not, is you're multiplying it by -1. We're going to use that idea to write an absolute value function without absolute value reference. And that's going to be something called piecewise. So if we can write an absolute value function without absolute value signs, the only way to accomplish it, everybody, is to write part of the function with one equation and part with the other. Let me explain. We're going to start off with something very basic. Write the piecewise function that represents the absolute value function. So how can I write this function so I don't have an absolute value sign? Okay, so follow this along carefully. This is tricky. If x in this function is greater than 0, do we need the absolute value signs? No. If x is greater than or equal to 0, do we need the absolute value signs? No. The absolute value signs are not needed. I don't know if you call it signs or sign. Doesn't matter. What did I do? Did I just delete my page? I must have. Are not needed. Oh, that's a pretty valuable piece of information, because you know what I can write then? I can write that f of x is equal to x as long as x is greater than or equal to 0. If x is greater than or equal to 0, then what's the function equal to? Well, it's equal to x, because the absolute value of a positive thing is just found by removing those absolute value signs. All right. If x is less than 0, oh, and by the way, maybe I better say this. I hope you get this idea, but this whole thing here is that. That's what that is. That's what that's saying. We don't need the absolute value sign, so we just write x whenever x is greater than or equal to 0. We don't have to write it in words. If x is less than 0, then the absolute value of x is equal to what? Well, go ahead. -1 times x. We don't. X is a negative number, but when I say x is a negative number, that negative is inside of the x. We don't go negative x. That would be negative of a negative number. It's a little tricky. But we're back to that idea that I started off today with at the top of your page, which is that if the quantity to be absolute valued is a negative thing, then you get rid of the negative somehow. And we can get rid of the negative by multiplying that thing which is negative by negative to make it positive. So that means that f of x is equal to negative x whenever x is less than 0. And that part of the piecewise function is this statement. Right? We're not, that's stuff that's written on the right-hand side. I'm not going to write that every time. It's just that for this first example, maybe some people need a visual of the words to understand what's going on. We're done. This is the piecewise function. F of x is equal to x wherever x is positive. F of x is equal to negative x wherever x is negative. I want to ask you guys a question, though. This negative x is negative x positive or negative? Who can tell me? Seamus.
Do you mean just the x or the negative?
I mean negative x.
Negative x would have to be positive.
Exactly, and that's the point. Because the absolute value has to give you a positive thing. So there's another negative inside of the x, and that's why Seamus said, are you talking about the x? Because the x is negative. Why is the x negative? Because we've said wherever x is negative. So that's the piecewise function. Now, let me show this to you graphically. And I don't want you to draw anything just yet. I'm going to rewrite the function here. We're saying f of x is actually equal to two functions. This is how we write it. One of the functions is x as long as x is greater than or equal to 0. The other function is negative x as long as x is less than 0. So I don't want you to draw anything yet. But if I graph the function y equals x, that's a pretty easy function to sketch the graph of. That means 0, 0, 1, 1, 2, 2, negative 1.8, negative 1.8. It is going to be a line that looks like, ugh, let me redo that. It is going to be a line that looks like this. This is y equals x. Are you with me? Okay. Where is x greater than or equal to 0? Well, x is greater than or equal to 0 on a number line at 0 and greater than it. That's x is greater than or equal to 0. You still with me? Okay, now look up here. The function is this piece as long as x is greater than or equal to 0. So I have a question for you. At this point right here, is the x coordinate greater than or equal to 0? Yes, it is. So it is part of the graph. Is this point a point where x is greater than or equal to 0? Yes. Is this point? Yes. Every point along this line from the origin up and to the right will be. Is this point part of the graph of the function? No. Which means that this blue shaded piece of the function looks like the following. Get my smartboard to cooperate. There we go. It looks like that. That's the blue piece. Now I'm going to draw this other piece in a different color so that you can see something that I think is important. I'm going to draw the second piece. Maybe what I will do is first highlight that blue piece. I'm going to draw the second one in green. Don't draw this just yet because you're going to have to erase stuff. If I were to look at the second function, the second function is y equals negative x, isn't it? Well, that's a line through the origin with a slope of negative 1. That is going to look like the following. Pardon the fluorescent lime. That is y equals negative x. But y equals negative x is only good if x is less than 0. Follow this very carefully. Is x less than 0 here? No, x is positive. This is not going to be a point on the second part of the function. Is x less than 0 here? No, that's not a point. And that means it's a circle. It isn't actually a point there. I'm just indicating that that's where it's not a point. Is x less than 0 in this region to the left? Definitely. Which means, and I'm going to go back to a better color, that the other part of the function is that green piece that I've drawn in. So the blue piece, which includes the origin, goes up and to the right, and that's the first piece of the function. The second piece of the function is the green one, which goes in the opposite direction up and to the left, and that is the second part of the function. We take a look at this on a graphing program. This is f of x equals negative x, but it's only valid wherever x is negative. This is f of x equals x, and it's only valid where x is positive. Notice it's the same graph we had yesterday. And this is a very simple example. Let's take a look at a slightly more complex example. Maybe before we do, have we answered this question? We've written the function in a piecewise fashion, and we've sketched the function. Any questions with that one? All right. So, y equals the absolute value of 2x minus 4. Here's where things get a little bit more abstract and tricky. All we have to do is say this. F of x, or y, let's go with y, will equal 2x minus 4 if 2x minus 4 is positive or 0. All this first statement is saying is, you know what? You don't need the absolute value signs if that function is already positive. And then y equals negative 1 times 2x minus 4 if 2x minus 4 is less than 0, because if 2x minus 4 is less than 0, the thing you're taking the absolute value of is less than 0, you got to multiply it by negative 1 to make it more than 0. Except that's not acceptable as an answer. We'll get to the graph later. What we want is to say 2x minus 4, and are you okay with me multiplying that negative 1 through? Why not? We could leave it out there. We could multiply it through. I'm going to multiply it through negative 2x plus 4. We want statements about x here. We don't want statements about 2x minus 4. So how do we get x? Well, let's talk, and I'm just going to go to a different screen here, about the 2x minus 4 is greater than or equal to 0. If 2x minus 4 is greater than or equal to 0, and we start to rearrange this, we see that 2x is greater than or equal to 4, and if you divide both sides by 2, you get x is greater than or equal to 2. So where is 2x minus 4 greater than or equal to 0? Where x is greater than or equal to 2. When we put the restriction, I call these a subdomain of the function. When we put the restriction or subdomain, we want to describe it in terms of x. If you take 2x minus 4 if you take 2x minus 4 is less than 0 and you rearrange it for x, you're going to get x is less than 2. So I don't want you to draw what I'm about to draw. I'm going to do my best here to give you different ways to visualize what's going on because it's difficult. This blue region, x is greater than or equal to 2, means, and don't draw this, x is greater than or equal to 2 means it could be here or to the right. This is what I mean by x is greater than or equal to 2. So if you were to sketch this function y equals 2x minus 4, any part of the function that's over there is going to be there. And any part that is not, we're not going to draw. So it's really too much to leave all these arrows and red lines on there, so I'm going to get rid of them. And this is why you have an eraser. If I were to sketch y equals 2x minus 4, and I just want to put it up here so we can look at it, y equals 2x minus 4 has a y-intercept of 4 and a slope of 2. Over 1 up 2, over 1 up 2, over 1 up 2. So we can start to get some points on here. And I could put down a ruler or freehand it. And if I did, but I don't want you to yet, because otherwise you're going to be erasing, I would end up drawing this line. But is every point on that line where x is greater than or equal to 2? No. X is only greater than or equal to 2 starting at this point and moving to the right. Which means what you draw is this. If I were to now look at the other function, which is y equals negative 2x plus 4, so now I'm looking at the second piece of the function. This has a slope of negative 2 and a y-intercept of positive 4. So the y-intercept is 4 and the slope is negative 2, which means you go over 1 and down 2, over 1 and down 2, over 1 and down 2, over 1 and down 2. You notice we're going to get that v, right? You have to, because it's the absolute value of a linear function. So what this graph would look like would be this. But we want to look at the green subdomain. Is x less than 2 everywhere on that line I've just drawn? No. Is it less than 2? Is x less than 2 right there? No, it is not. It's equal to 2. It's not less than 2, which means that that point on this other side of the function doesn't exist there, but luckily that point exists for the right-hand side. So it fills in that opening. It's seamless, even though there's kind of a break in there. All of this stuff, x is greater than 2, so we wouldn't include it, which means this is what it looks like. Any questions with B? Sorry. Any questions with B? F of x is the absolute value of 1/2 x plus 1. Okay. Well, that means that f of x will be equal to 1/2 x plus 1 in one part of the domain of x values, and it will be equal to negative 1 times 1/2 x plus 1 in another subdomain. How do we determine the subdomain? We basically take the thing inside the absolute value sign, set it greater than or equal to 0, and solve for x. If I subtract 1 from both sides, I'll get 1/2 x is greater than or equal to 1. If I multiply both sides by 2, I get x is greater than or equal to 2. My mistake. When I subtract 1 from both sides, I get -1. When I multiply both sides by 2, I get -2. So that means when x is greater than or equal to -2, this is the function we use, 1/2 x plus 1. When x is less than 2, then we use the negative of the function inside the absolute value signs. By the way, the equals always goes with the piece that you just removed the absolute value signs from. So I'm going to just draw 1/2 x plus 1 in yellow. 1/2 x plus 1 has a y-intercept of 1, and it has a slope of 1/2, which means you go 2 to the right and 1 up, 2 to the right and 1 up. It's always rise over run. So 2 to the right and 1 up, 2 to the right and 1 up, 2 to the right and 1 up. You will notice, I hope, that this number is always going to be the x-intercept. And I forgot to put negative here. I apologize. That is definitely negative. That number is your x-intercept. So if I were to draw, that's not a very good line. I want to redo that. I thought I was on a different tool. If we were to draw that line, is every point on that line in this domain? No. Only the points at -2 for x and to the right are in there. So the fact of the matter is, the first piece of the function looks like that. How many of you see the second piece is going to start at that point and go to the left at the same angle? You don't need to do it this way, but I'm going to. If I were to look at the second piece, which is y is -1/2 x minus 1, I will do this one in blue. Then the y-intercept is -1, and the slope is -1/2, which means I go over 2 and down 1, over 2 and down 1, opposite direction. Opposite direction, opposite direction. So if I were to draw this, it would look like that. Is every point on that line where x is less than -2? No. None of this stuff is where x is less than -2. And in fact, this isn't even where x is less than -2, but it's filled in by the other piece. Yeah, well, I don't want to go away. So what the graph actually looks like is that. I kind of went off the rails there near the right-hand side, but you get the idea. Still good? Okay. Now things take a turn. Because a linear function, which is everything we've been dealing with, will only have one x-intercept, it only has two subdomains. Because a line drawn is going to have one piece that's negative that has to be tossed upwards. But a parabola can have two pieces that are negative that each have to be tossed upwards. Or maybe the middle piece is negative that has to be tossed upwards. So what we're going to do is write this as h of x equals x squared minus 5 and negative of x squared minus 5. But we need to know, this is the tricky part, and you don't know how to do this algebraically. We need to know where this thing is greater than or equal to 0, right? In terms of x. And I don't want you to rearrange that. You cannot rearrange a quadratic inequality. It doesn't work. But what you can do is look at this as a graph and use the x-intercepts and your knowledge of the quadratic function to tell me where it's negative and where it's positive. So for example, if I were to look at y equals x squared minus 5, which is not the question, and I solve this for an x-intercept by letting y equal 0, I can write x squared equals 5, which means the x-intercepts are plus or minus root 5. I hope you recall when I said this number, and I underlined it in green, is always the x-intercept. So we're looking at x-intercepts. So what does this graph look like? Not this inequality, but this graph. What it looks like is a parabola that opens up because it's positive x squared, passing through negative root 5 and positive root 5 on the x-axis. And I mentioned this yesterday or the day before. You're going to be working on some of this stuff in this chapter where you will think you will have it in your head. What I told you makes sense. You followed along. It made perfect sense. You go to do it on your own, and all of a sudden your brain screeches to a halt because something doesn't make sense. It's tricky. My question right now is, where is this true in terms of x? Where is the function x squared minus 5 greater than 0? Where don't we need the absolute value signs? Well, we don't need the absolute value signs any place the function was above the x-axis. So what can we write there, Isaac? You know? Is this thing, which is y, this is very tricky, is this thing, which is y, greater than or equal to 0 there? No. This thing is only greater than or equal to 0. This is going to require a lot of thought on your part. Here, it's equal to 0. Better use a different color. It's equal to 0 here. It's equal to 0 here. And it's greater than 0 here. And it's greater than 0 here. And we're kind of now going in circles, because I'm telling you the absolute value sign is not needed if this, which you were absolute valuing, is greater than or equal to 0. And yesterday we said you don't need to worry about the absolute value if it's already above the x-axis. Okay? This is tricky, and I can tell because some of you are going, you think you have it, and then it's just slipping away. These two green pieces are where x is less than negative root 5 or equal to it, and where x is greater than or equal to positive root 5. That's the domain where, when you go from negative infinity all the way up to infinity, where is the thing above the x-axis? Well, everywhere from negative infinity up to and including negative root 5, and then everywhere from root 5 to infinity. Where is it below? Well, I'll get to that in a second. But those are the two domains we have to put here. When x is less than or equal to negative root 5, and x is greater than or equal to positive root 5. Yes?
So, when it was a linear equation, we were making up these beats, right? So does that, and the other equation, which needed the absolute value sign, was going off into the negative direction. So does that mean that because the other equation needs the absolute value sign, is this going to be the reverse of the downward arc of that parabola?
Exactly. This is a very complicated way to do what we were doing yesterday, which is to simply take whatever's below the x-axis and fold it up. Okay. Where on this graph, so these domains here that I'm writing up top, these are where x squared minus 5 was already greater than or equal to 0. Where is x squared minus 5 less than 0? Well, it's not less than 0 here, and it's not less than 0 here, but it's less than 0 everywhere in between. And don't forget, if it's less than 0, we're going to take x squared minus 5 and multiply it by negative 1. Well, that's just going to flip it up. It's going to reverse that parabola. If I multiply x squared minus 5 by negative 1, it would do this. So that bottom part of the parabola is being multiplied by this negative 1 every place x is between negative root 5 and positive root 5. And you will probably notice that in the process here, I've basically given you the picture of the graph. If you were to sketch, I guess we should know what root 5 is. Let's calculate root 5 even to 1 decimal place. Lynette, 2.2 approximately. So root 5 will be here. Negative root 5 will be here. I'm going to move this a little bit out of the way for us. Again, this is tricky. I want to go slow here. If I were to sketch y equals x squared minus 5, it would look like this. Don't draw this. X squared minus 5 would look like this. Is x squared minus 5, let me ask it a different way, is the absolute value of this graph needed, say, here? No, because y is already positive. Is the absolute value needed here? No. What this means is any place the absolute value is not needed will be this point and above. This point and above. So that red thing that I just drew, that's the first piece of the function. When x is negative root 5 are to the left, when x is positive root 5 are to the right. Is, going back to this which I just erased, is the absolute value needed here down below? Yes, it is. And how do we handle that? We remove the absolute value and multiply everything by negative 1, so everything gets folded up. Which means that these two things together are the absolute value of x squared minus 5. The two red arms are where the absolute value wasn't needed. The green hill is where the absolute value was needed, and we multiplied by -1, which pops it above the x-axis. This is not tough like algebra tough. This is tough, conceptually tough. Because we end up talking about where y is positive or negative, but we describe where y is positive or negative by talking about x, which is a real puzzle. Yep.
Can you write after like the first x squared minus 5 comma x is greater than or equal to the negative square root of 5? Can we not write x is greater than or equal to positive or negative square root of 5, or do we have to write both of them individually?
You have to write both of them individually, and the reason is because one of them is less than or equal to and the other is greater than or equal to. Right? If they were, and they never will be both greater than or equal to or both less than or equal to. Does that answer it?
Yeah.
Okay. Let's try one more. And I'm not worried so much about the graph of the function so much as the piecewise part of the function. This will be broken into two functions. One of those functions will simply be the original function. In fact, you know what? Let's not worry about graphing this on paper. Let's use our graphing calculator. And one of which will be the negative of that. And I'm going to take the liberties here of just multiplying it by -1. You know how I would normally write -1 times it? Well, all that means is I'm going to switch the signs. So we want to know the listen carefully to the words. That bottom function is -1 times the original. We want to know the domain of x values over which we don't need the absolute value. We want to know the domain of x values where the function was either on the x-axis or above. Does this parabola open up or down? Down, right? So think about this for a second. This parabola is going to open down. If the x-axis is here, then this will be from here, including that point, to here. This will be where the absolute value is not needed. It's going to be some number is less than or equal to x, which is less than or equal to some number. I'm going to try to make this general. Let's say that number is a and this number is b. In that case, we wouldn't need the absolute value signs when x is less than or equal, when a is less than or equal to x, which is less than or equal to b. We wouldn't. Would you agree that the absolute value signs are required here? Okay, so we would have to take -1 times the function if x was less than a or x was greater than b. Going back to your question or query, Kendra, the two arms always have to have two separate statements. You can't mix them together somehow. So you know what this problem boils down to is what are the x-intercepts of that function? Why don't we just look at our calculator? Let's cut ourselves a break here. And I'm not looking at the absolute value function. I'm just looking at the parabola itself. Excuse me. So y is equal to -0.5x squared plus 2x plus 6 Zoom 6. Looking like it's crossing at -2 and 2, 4, 6. We can confirm that, everybody, by going to our table and looking at 6, which gives us a y-coordinate of 0, which means it's an x-intercept. And by looking at -2, there are algebraic ways to determine the x-intercepts. I'm just saying, you know what? It's 10 to 3. It's been a long day. Sometimes we want to just take a break. So that means, everybody, that this is a parabola without the absolute value signs, which crosses at -2, crosses at 6, opens downward. So where are the absolute value signs not needed? They are not needed from here up to and including here, because the graph is already above the x-axis or on the x-axis. Where are the absolute value signs needed? They are needed here and to the left and here and to the right, because that's where x-wise, y is negative. That's the tricky thing. You talk about where y is positive by telling me about x. So -2 to 6. We didn't need the absolute value signs there because that was above. And, you know, sometimes the part where you don't need it is the middle part of the parabola. Sometimes it's the two arms. Depends on whether it opens up or down. Where is the graph below the x-axis, which would mean that the absolute value signs are needed, which would mean the function is -1 times the original function? That's where x is less than -2 and where x is greater than 6. Again, the equals to always goes with the first part of your function, where the absolute value signs can just be kicked over the boards because we don't need them, because y is already positive. It's tricky. Bottom line, forgetting about graphing, one of your functions will always be f of x, and one will always be negative f of x. And this is where x-wise, do you understand what I mean by x-wise? I want you to tell me about the domain. Where x-wise, the graph of f of x, without the absolute value signs, just looking at the graph, where it's above the x-axis or on the x-axis, that's the domain that you have to figure out that always goes there, always. And the domain that always goes here is where x-wise f of x was below the x-axis. And, you know, quite frankly, I think the deeper understanding is that. How you find where it's above and where it's below, I really don't care. But the defining points of all of your domains will be x-intercepts. You have to look at the x-intercepts because that's where the graph goes from being below to being above, or being above to being below. It's pretty greasy stuff intellectually. Page 337, page 377, 9 to 14. Is that what I have typed out in your handout? Okay, so that's the set of suggested practice problems. You've got about 15, 20 minutes here. It's taxing on the brain, but take a breath, get your head screwed on straight, and get to work on these. And get it solidified more in your brain now before you leave. Don't leave it till later. It's just been pointed out to me that when you take a look at example E, on the print copy that I've given you, you're missing the squared on the x. So just to let you know, what I have on the board is what we should have had. Thank you.